Thanks for the wonderful introduction, Dave. And I'm not going to be able to use that because Meta won't let me use a flash drive to export my presentation. So bear with me, guys. I'm just going to open up the computer, get AV going, and we'll get started. All right. We good to go? All right. Well, thanks again for the nice introduction. I really appreciate it. Ben Cook. Some of you may be wondering why Meta's here today. Well, it's actually because Jim Reed gave me a call and offered a lifetime supply of cavity SOI, but that's besides the point. But actually, one of the things I've found surprising is calling all the suppliers in the MEMS and sensors industry now that I've moved to Meta, the first question I get asked is, aren't you guys a software company? What are you guys doing calling us? So to give you guys a little bit of a background and history here, we bought Oculus, which is one of the leading VR platforms, in 2014. And at the same time, Mark established a research organization for hardware called Reality Labs Research. And that's the organization that I'm part of and that my team is part of. So goal number one today, make sure all of you guys leave with the message that Meta now does hardware. So remember that, write that down in your notes. So what are we trying to solve at Meta in the AR and VR space? So if we look at the spectrum of devices that we've been innovating at in the industry over the years, we take a spectrum of devices that have moved towards portable devices, right? So we started with cinema. I'm not going to go back to the day of the phonograph, but we started with cinema, and we've slowly matured devices to where they've gotten smaller, more personal, and more portable, right? Now, as we've gone that direction, one of the things that we've lost is the immersiveness, right? So if you go to an IMAX theater today, you're in a very immersive experience. But if you're on a smartwatch, while it's portable, it's very personable, it's not extremely immersive. So one of the challenges we're trying to solve is bring the benefits of all the miniaturization that we've done in this industry to make things more personal and portable, but bring the immersiveness back to the experience through AR and VR. So last October, our CEO, Mark, announced a pretty big vision for the metaverse. And while this vision isn't necessarily new, it's been around for decades, the technology is finally there to start realizing this vision, as well as the investment from industry. I think you guys have probably seen our financial reports. People call out how much we're investing. There's a lot of other companies across the industry investing in AR, VR, and the metaverse and the technologies to get there. So it's a really exciting time. And while the specifics are still unknown of exactly what the metaverse is, what we do know is all the technology needed to be developed for AR and VR is going to require a lot of innovation across the industry. And this industry specifically will have some pretty major impacts on the future of AR and VR. So let's take this example, which Mark called out in his keynote a few years ago, which is an AR chess experience. Let's talk about some of the grand challenges we're going to need to solve to enable an experience like this. So if we dissect it, the first thing we're going to have to do is develop optics and displays that can be both portable and immersive, right? You want an optics and displays not like a cell phone screen, but one that you can wear that makes you feel immersed in an AR, VR experience while also being able to be worn all day. We're going to have to develop the compute power to do that on a wearable platform. Today, this has to be done on NVIDIA graphics cards, on servers. We need to drive all that compute into a platform that's portable and wearable. We need to develop the sensors to give us the context of the environment, to know exactly where the table is, the chair is, what the users on both sides of the platform are doing so that they can play chess together, and the compute platforms can understand where they are and what they're moving. We need to develop actuators that bring the sense of touch to this platform. So when I grab one of those chess pieces, I feel it. I move it across the table, I know it's landed. We need to develop holographic imaging and graphics platforms that bring reality to these types of displays. Ergonomics are important. You don't want to be wearing one of these big VR headsets all day, right? So we need to bring these platforms to something that's socially acceptable, comfortable, and wearable for an all-day use case. And finally, interactions. We need to enable interaction devices that don't require you to tote around a mouse, a keyboard, or pull out a cell phone, because that ruins the whole sense of interaction and immersiveness in the experience. Now, I could go through all of these, but it would take probably the rest of the day. So I'm going to focus on interaction devices for 2 reasons. Number 1, because that's where the main focus of my team is. And number 2, because there's a lot of MEMS and sensors innovations needed in this space to enable those natural interactions for an immersive experience. So let's take a step back. If we look at how we've interacted with compute platforms over the last 60 years, we started off, we'll ignore punch cards. I wasn't around for that time. We started off with keyboards, right? Very mechanical devices. That was in the 60s. We had command line UIs, again, before my time. We get closer to my time, the 80s, where we started to have the first graphical user interfaces, and the mouse came on board, right? And the original mouse was essentially a roller wheel and a click button, but there was a lot of innovation in MEMS and sensors, things like LEDs, speckle sensors that enabled us to miniaturize and really bring the mouse to the mass consumer. The 2000s, we moved on to touch screens, cell phones, and natural app-based UIs. And their innovations in capacitive touch, strain touch, ultrasonic touch all enabled us to miniaturize new interaction modalities for cell phones. And today, as we see the emergence of AR and VR, our hypothesis is that we want our interaction devices to be on the body and as seamless as an interaction you would make with a surface or any other normal, natural interaction you would perform on a daily basis. So, with that being said, I'd like to lead off with a video from my colleagues where they're talking about how they believe the future of interaction devices will be for the first paradigm I'm going to talk about today, which is everyday AR. So that's an experience where you're walking around, messaging, calling, maybe using navigation. So a less immersive experience, and then we'll go to a second paradigm, which is a very highly immersive experience and how we do interaction for those paradigms. So with that being said, I'll hand it over to my colleagues. Do we have audio? We had it working. I hope I don't have to narrate this whole thing. I put it in there specifically so I didn't have to talk. It's playing. Sorry? It's plugged in. Okay, well, I'll try and narrate while they're trying to figure this out. But essentially what my colleagues are talking about right now is the fact that our hypothesis is that as we want interaction devices to be natural and worn on the body, we want them to be neural based. Right, so typically in the past, our sensors have been inertial, they've been stress, they've been humidity, they've been pressure. Oh.
Is when they work right, and we still have a lot of work to go here, feel like magic.
So if you send a control to your muscle saying, I want to move my finger, it starts in your brain, it goes down your spine through motor neurons, and this is an electrical signal. So you should be able to grab that electrical signal on the muscle and say, oh, okay, the user wants to move their finger.
What is it like to feel like pushing a button without actually pushing it? And that could be as simple as, hey, I just want to move this cursor up or move it left. Well, normally I would do that by actually moving. But here, you're able to move that cursor left. And it's because you and a machine agreed which neurons mean left and which neurons mean right. You're in this constant conversation with the machine.
This new form of control, it requires us to build an interface that adapts to you and your environment.
Everything starts with a click.
The intelligent click is the ability to do these highly contextual actions in a very low friction manner.
It's kind of the purest form of a superpower. You are in control, but the system is exactly inferring the right thing for you to control. All you have to do to operate it is just click.
So for example, if I'm cooking and I'm kind of pulling some noodles out of a box, the interface could ask me, would you like to start boiling the water? The wrist can also be a spot where the technology is communicating back to the user.
The haptics, the sensation of touch around us, this is part of how we learn and use motor control is critical to AR and XR.
We wondered, as you pull back the bowstring on a bow, if we tied that not to the tension growing on people's fingers, but rather squeezing on the wrist, would it add to that experience like you're pulling back the bowstring? The answer is yes.
That future, it really is the computer that is seamlessly integrated into your day-to-day life. The next computing platform is the mixed reality platform, the one that really totally blends your virtual environment and your real environment in a seamless way.
We're in this moment where we can move from personal computing to personalized computing.
What if you and a computer agreed to design a keyboard together, and you type faster on it than anybody else in the world could type on your keyboard?
I think what this enables is the ability to not have to focus on a computer, on a phone, and be able to still interact with other people. It's going to open up a new generation of communication and access and navigation.
It leads to this phenomena of increased agency, of you feeling like a level of control you've never had before. We want computing experiences where the human is the absolute center of the entire experience.
Pretty cool, huh? I know I was in disbelief when I saw that video before I actually got to try the technology. So what you guys saw there was one of our first research prototypes for neuromotor input. So you can see the wristband here in this image. And the technology that's being leveraged here is something called EMG, or electromyography, specifically surface EMG. So what you can see here is the wristband has 16 pairs of electrodes which contact your wrist. And as the neural signal travels down your motor neuron to your hand, saying you want to move your fingers, these electrodes pick up that signal, and ML then decodes what you specifically wanted to do. And what I'm going to show here are some specific examples of the technology working. So what you'll see is in the very top left, there's the user's hand, and you'll see how little it's moving. On the far left side, you'll see all of the voltage signals being acquired from all these different sensors. And on the right, you'll see the game that the user's playing, which is essentially trying to click all the green boxes. So as you watch, they're very gently moving their thumb and then squeezing their hand to do a click. And what you notice here is there's an extremely high level of control, even though the user is barely moving their hand. So you can imagine all the use cases that this could be valuable for, whether it's controlling a computer or having your hand in your pocket when you're cold and doing control of an AR experience. But then we can go to much more complex interactions, right? So this is essentially a mouse-like interaction, but you can imagine, it's great to have a keyboard too. So in this demo, what you'll notice is there's 2 wristbands, one on each wrist. The wristbands are reading the signals coming down both hands, and the user's actually using his legs as a surface for a keyboard. So you can imagine carrying a keyboard anywhere. So what you'll see here is the user's moving their fingers, and the ML algorithms are actually decoding his own personalized keyboard. All right, so it's personalized ML to your own neural signals, and it's decoding exactly what the user wanted to type. So you can imagine now you've got a mouse and a keyboard in your pocket with just a neural wristband. Now, that being said, there's a lot of challenges with neural interface. One of the things is it does have to be personal. Everyone's neural signals are different. So the ML needed is pretty intense. There's also a problem with EMG, which is we have to have skin contact at all times. So there's a lot of innovation that this team can be doing on neural sensor interfaces, specifically around how we better measure electric and magnetic fields for sensing neural axon fires to enable us to break some of those design spaces that we're linked into today. So that being said, some of the other sensors that we're looking into are non-contact, more traditional sensors to do sensor fusion with biomimetic or neuromotor sensing. So here you'll see an example of another interaction wristband where we have IMUs, optical sensors, and VT-based haptics to try to mimic some of those same interactions with the goal of doing sensor fusion to mitigate some of the challenges with neuromotor sensing. So I'm going to show you a second video here of interactions using only sensor fusion of traditional sensors. Now, one thing you'll notice is it's not quite as powerful, but you can still get a lot of the interactions done that you would need for an AR or VR experience.
In this demo, I can pull up the app menu with a quick wrist roll. We use subtle wrist angles to control the cursor and pinch to select. This is done with minimal motion and with my arm at my side. In the camera app, I'll use pinch again to snap photos. Then, I'll wrist roll again to switch to the photo gallery. Wrist tracking can also be used for gestures, such as wrist flicks. Here, I'll use wrist flicks to navigate to a photo I took, and I'll select with pinch. Before sharing, I can mark up this photo using my wrist angle to draw, and pinch to toggle pen up and pen down. Then, I'll share the photo to Instagram. Wrist angles let me scroll through this Instagram feed in a smooth and intuitive way. I can start and stop scrolling with a pinch. I can double pinch to like a post. And I can long press with a held pinch to open a reaction menu. In this menu, I'll use thumb swipes to move left and right between options. And I'll use thumb tap to select.
One thing I'd like you to notice in this video is how much more the user has to move their hand with a traditional sensor suite using
Finally,
sensor fusion.
I'll switch to a 3D interaction, where I use wrist tracking to control this drone through an obstacle course. We could layer in spatialized haptic feedback to let me feel as my drone flies through each hoop.
So overall, it's a pretty cool new paradigm of interaction, thinking about moving from a touch screen or a mouse and a keyboard to being able to wear devices that can infer what you want to do. And that's going to open up a whole new level of HCI, or human-computer interaction. But as you guys saw, there's still a lot of challenges. On one side, we're making the bet on neuromotor input, which still has a long way to go. There's a lot of maturation that needs to happen within this industry from a sensors perspective, from a sensor fusion and ML perspective. We need to work on ways of bringing haptics and rich haptics to these types of bands, moving beyond traditional LRAs, which are large vibrotactory devices, to ones that can give you a sense of touch all the way around your wrist or on other parts of the hand. Again, sensor fusion and edge compute is going to be extremely important. As we start needing more and more ML to make sensor fusion happen, we're going to need, let me close that box really quick. Apparently I have a work meeting right now. So as we need more ML, we're going to need more compute power, better sensor fusion algorithms. And one of the other things that you notice here is I wouldn't want to wear this wristband. We really need to start miniaturizing and looking at wearability and swap or size, weight, and power for these types of devices. So I mentioned we're going to talk about two paradigms. The second paradigm, and this is the more fun paradigm for me, which is highly immersive interaction devices for AR. And what I mean by that is when you're in a VR experience today, you have two controllers in your hand. They're a little bit unwieldy, and they give you some haptic feedback sometimes. But what if you could put on a glove that would allow you to interact in VR, where you could grab this surface, even though it was a virtual surface, and it stopped your hand, and you could feel the texture. You could shake someone's hand in VR. Well, that's one of the other interaction modalities we're working on. And I'll show you a quick video here on one of our first prototypes.
Got you. Good try.
Pretty cool, huh? It's actually, it feels pretty awesome when you get to play with it. But again, you'll notice this is a Frankenstein glove today. This is not something that is ready for prime time. But when you look at this glove, it's pretty amazing. So I'll show you this on the next slide, but we've been developing very fine tactile haptic displays which can essentially mimic the feel of a surface. And this is kind of a new paradigm for soft MEMS and how we start applying them in consumer products. We're working on touch sensors and how you can actually, over the entire surface of the glove, understand what the user would be feeling in a virtual environment. So what's the pressure? What's the strain? What's the temperature? If I touch a real surface, how do I communicate what that real surface feels like to the computer so that can be transmitted then to someone else in VR? So highly dense sensor networks are needed across these wearable textiles to enable that type of understanding. Today we're using macro scale pneumatic and electrical wiring, but this needs to be miniaturized with MEMS so that we can really drive a consumer product. And one of the cool things you'll notice here is this is all integrated on a textile platform. So one of the other things I'll show you is some of the work we're doing on smart textile integration to really make these devices wearable. So here's a quick video of, on that fingertip, what this looks like behind that black pad, which is a highly dense pneumatic bubble array being driven by pneumatic computers. So just like we have electric computers today that use transistors to switch on and off electric actuators, we're driving technology to also be able to do compute in the pneumatic domain to enable very rich haptics on the hand. And like I also mentioned, we have an entire textile research team that's working on functional textiles or engineered textiles, which are pushing us beyond the domain of standard textiles like you wear today, but start incorporating things like highly dense electrical routing, pneumatical routing, and interconnects to MEMS sensors and semiconductors so that we can have fully functional wearables that also feel comfortable and look good. So again, there's some pretty grand challenges for fully immersive experiences as well. Again, like I said, this glove is a Frankenstein today, and you guys can see the level of miniaturization that's needed. We need to move to even finer micro haptic displays. We still haven't reached the retinal display for haptics today, like we have with the visual display. We need to get to scalable sensor nets that can cover huge areas like this, but also rapidly transmit those amounts of data over backplanes. We need to understand how we do MEMS sensors and soft goods integration. I mean, we've lived in the hard, rigid paradigm for so long now that we take for granted some of the stress mitigation impacts and reliability impacts it has on devices. Once we go to wearable devices, that's a whole new set of problems we're going to need to solve as an industry. And again, edge compute and wearability and swap are always front of mind for these consumer products. So this is my final slide and kind of a call to the folks here, which is, we believe interaction for AR and VR, and AR and VR in general, are going to be human-centric and wearable. And that kind of changes the paradigm of some of the innovation we've done in the industry over the years. And it's going to add a lot of challenges for us for the next decade. And one of the things I'm really excited about is working with all the folks in this room. I see a lot of folks here that I worked with in my past life. I'm really looking forward to working with all of you guys to solve these challenges. So thanks for having me. Thanks for the great introduction. Thanks for the lifetime supply of SOI, Jim. I'm just kidding. And look forward to the rest of the talks today. Thank you.
Thank you very much, Ben. Really appreciate it. Great presentation. We've certainly got beyond the whole good morning computer phase of technology, haven't we? I won't even attempt the Scottish accent, but I mean, this is fantastic things. I'd like to open up the floor for questions as we go through this. I would also like to introduce, I think we've all been through it before. We have 2 microphones, 2 open microphones. As you have a question, could you please step up to the microphone so that everybody can hear you? It really helps out a lot. But are there any questions for Ben at this point? Mr. Free SOI Wafers.
Yeah, we'll have to discuss that offline. Anyway, no, I think it was fantastic to show, where we are now. I mean, I think that sometimes we forget how much innovation has already happened and what we have at our fingertips. But what I wanted to maybe have you expound upon a little bit is that you talked about some of the form factors that you're looking at, and obviously, we have to get it that it's much more user-friendly for these haptics that you're talking about. So could you maybe share some vision, would it be clothing kind of things, or, almost like a vinyl glove you use in the clean room, or what is your vision, and what's the time frame you think?
That's a great question. So I think the first one on vision, I think generally we're going to see a lot of things for the consumer market start to move towards soft. I think that's just a general trend, right? I think we live in a silicon world, we live in a rigid world as MEMS and sensors folks. We've seen, over the last decade or so, the healthcare industry start to move to some of those paradigms for microfluidics, for example, or biosensing. I think we're going to start to see a proliferation of that coming into the consumer market to make things that are more human-friendly, right? Hard things are not as human-friendly as soft things. So I think we're going to start seeing smart textile, smart wearables, a lot more proliferation of the smarts into those wearables, but that comes with all of those challenges. And what was your second question, Jim?
The time frame.
Time frame? Oh, I'd love to see some of these things start to hit the market in the next few years. I think to get to things like these gloves in a consumer form factor is probably another decade. That's my guess. Yes?
There's a lot of neural signals that you talked about collecting in order to make your devices work. How do you account for neurodiversity in the user?
It's a wonderful question. And I'm probably not the right person to answer that because that's not my expertise. We luckily have a lot of neuroscientists that I work with. But I think it's one of the key challenges we see, right? Neurodiversity is a real problem. It's a problem within user from day to day. It's a problem across the population because everybody's neural signals for the same interaction are very different. So that's one of the areas where we're really working on co-learning with ML, which is how do you train the ML with the user to really understand what they're trying to do. And I think sensor fusion with a lot of the modern sensors we have today can be used as aids to help in that co-learning process.
Okay, thank you.
And sensors and everything in a room is one thing, but having that interactive experience with global players in gaming environments and everything will also mean that the latency is going to be a very, very important thing, right?
Yes.
What is Meta's play in this?
That's a great question. So this is why I called out edge compute a few times today, right? So I think there's 2 parts to latency. One is the network relationships you have. And I think if you look at most of the gaming platforms today, they've solved this sub 50 millisecond latency problem that's needed from a network perspective. But the other part of that is once this for example, highly rich haptic data gets to your glove, you don't want to have to send that data off to a cloud, send it back to your device, and then have to do all the computation, right? You really want to be able to do compute at the sensor, compute at the haptics, at the device with the minimal information transfer over the network as possible. So one of the areas that I'm really bullish on is driving as much compute, distributed compute and edge compute towards the sensor and haptic as possible to reduce that latency.
Good. Thank you.
Okay, any other questions before we move on? I thought it was a great presentation. Thank you very much again, Ben, for your time here today and for reintroducing the group into the organization and coming down to visit. We very much appreciate the presence, and have a great day. Have a great week.
Thanks for having me, Dave.
Thank you.
Thanks, everyone.